Hello class, I wanted to go over section 4.1 in its entirety in this video. So let me start this slideshow. That way you'll be able to view it when you would like to, and then take notes as accordingly. So section 4.1 was on scatter diagrams and correlation, and we went over this, but the response variable, that was the dependent variable, the variable whose value can be explained by the value of the explanatory variable, or the predictor variable, or the independent variable. And as such, the explanatory variable is typically on our x-axis. I shouldn't say typically. Is on our x-axis, and the response variable is on the y-axis. The scatter diagram or scatter plot, that's a graph showing the relationship between two quantitative variables. Alright, so we see here we have the x-axis, y-axis, and then just a whole bunch of points here graphed on the scatter plot. And I'll show the instructions on how to do it instead of StatCrunch, but those are posted on Blackboard for all of you. So for example, this example number 1, I have a golf pro wants to investigate the relation between the club head speed of a golf club in miles per hour and the distance in yards that the ball will travel. He realizes other variables besides club head speed determine the distance a ball will travel. To eliminate the variability, the pro uses a single model of club and ball, one golfer, and a clear 70-degree day with no wind. The pro records the club head speed, measures the distance the ball travels, and collects the following data. And we want to draw a scatter diagram of this. Now I have this in my link on here, but just to go over the process, if you will, let me actually pop into StatCrunch for that. I have my data that I need to copy into there. In one moment. And actually I need those headers in the bar on top. Okay. This is underneath graph Scatterplot. It's kind of on the middle of this list. The club head speed was our explanatory variable, so that's the x. The distance was the response, that being y. Everything else on here is optional. And then I'll hit compute. And we're given that graph, right? And it shows that graph on there. And this link would actually open up that same graph if you want to see it on there. Now we can interpret these scatter diagrams a bit. We can have a positive association, negative association, no association, a nonlinear association, all different types. So a positive association, that's two linearly related variables both increase. A negative association, that's two linear related variables where one increases, the other decreases. No association, you can't really discern a trend. So it doesn't really go up or down, just stays practically constant. Nonlinear association, that basically is not a line. It can be any other type of function, as long as it's not a line. So these first two here are both linear. Okay, this one goes up on both the x and y axis. So this is a positive association. And this one's a negative association because as x increases, y decreases. This last one here is a no linear relationship. It has no relationship at all because, well, we can't really see any type of increase or decrease for either the x or y variable. But these two, though, even though they're not lines, they're nonlinear, they do have a type of association. This one has a quadratic, this one has a cubic. We can draw lines in there, but they're not going to really be representative of the entire graph. So do bear that in mind. The linear correlation coefficient, or also known as the Pearson product moment correlation coefficient, this is a measure of the strength and direction of the linear relation between two quantitative variables. It's denoted by this Greek symbol rho for the population correlation coefficient, or R as the sample correlation coefficient. And we could do that calculation as the sum of the products of the z-scores of the x variable and the y variable divided by n minus 1 for that degree of freedom. And again, this particular calculation in and of itself can get complicated if we have any number of data points, which is why StatCrunch could do that for us, or nicely. We do have a bunch of properties for this, being that the correlation coefficient must be between -1 and +1, inclusive. If we have a +1, that's a perfect positive linear relationship. If it's -1, that's a perfect negative linear relationship. The closer it gets to +1, the stronger the positive association. The closer it gets to -1, the stronger the negative association. And if it approaches 0, as in if it's like very close to 0, then there is no evidence of a linear relationship. The correlation coefficient is unitless, a measurement of association. It is not resistant to outliers, but that's a topic we're not going to really delve too much into in this class. A perfect positive relationship is like this first graph. This will have a correlation coefficient of exactly 1 or thereabouts. A strong positive linear relationship has a correlation coefficient of about 0.8, 0.9. All of the data points are on roughly the same line, and they have the same overall trend. The moderate positive relationship, this has a correlation coefficient somewhere between 0.4 and like 0.6 or so. The data points are kind of spread out, but they follow the overall trend. And I drew a low positive one up here. Again, they follow the same trend, but they are much more spaced out. Again, they do have that overall trend of an increase, but it's a little bit harder to discern. And this has a correlation coefficient of about 0.1 to like 0.3. For a perfect negative linear relationship, that has a correlation coefficient of about -1. The strong negative has a linear correlation coefficient of about -0.9 or -0.8, thereabouts. And as you can see, the data points are pretty close together. They follow the overall negative trend. The moderate negative linear relationship, this one is a bit more spread out, but again follows that same trend. And this is between -0.4 and -0.6. For the low negative relationship, again, even more spread out, but it does still follow that negative slope. It has a negative correlation between -0.3 and -0.1 about. A correlation coefficient close to 0 like this one has no linear relationship. As you can see, you can't really discern any type of pattern of increasing, decreasing, or anything, since the points are all spread out in every which way. This last one here is a nonlinear relationship. This would also have a correlation coefficient close to 0, but unlike this last one, we could put a line in to show the overall idea, but it's not going to really describe most of the data too well. Now, we could go and compute this instead of StatCrunch. It is underneath Stat, Summary Stats, Correlation. And it's using the same data set as what we had for example 1. So I'm going to switch to StatCrunch very quickly in order to show that for all of you. And yes, I want to keep all my annotations. since I write so much as it is. Let me keep my Scatterplot on here. For this, we're going to Stat, Summary Stats, and Correlation. The order of this does not matter for the correlation coefficient because it will be the same thing anyway. But this gives us a value of 0.939 that rounds to about. And as you can see, the data here pretty much is in a straight line. There's a couple of data points outside of it, but it follows the overall trend. It's pretty strong. Hence why we have that type of correlation coefficient, as we described on here. When it comes to determining if we do have a linear relationship, we could test that using this process. So we first need to find the absolute value of the correlation coefficient. Although if it's already positive, like this last one was, finding the absolute value of the correlation coefficient is still going to be positive anyway. We want to then find the critical value in Table 2 from Appendix A for the given sample size. If they want you to use it, they'll give it to you. I'll show you that in a moment once we get to an example. And then if the absolute value of the correlation coefficient is greater than the critical value, then we would say a linear relation exists between the two variables. Otherwise, no linear relation exists. So if we have a positive critical value here and a negative critical value here, then we have a positive association if it's above that critical value, or a negative association if it's below that critical value, and then no linear relationship between them. So to give an example of that idea, I have example number 3 here, and that's to determine if there is a linear relationship between club head speed and distance. I mean, we already saw it in the example, but just to show this process. We take the correlation coefficient of positive 0.939, take the absolute value of that. That still makes positive 0.939. And we could count the number of entries in here. There's a total of 8. And then we need to open up that critical value table. And I do not have that open anymore. Lovely. Let me go open that. In my long list of options, let me actually just very quickly get that up on here. Which will hopefully now go any moment. Not that one. There we go. So this is the critical values table. That's just going to load in the Adobe Reader as I'm speaking. But if they want you to use this, they'll certainly give it to you. I'm just going to show it to you now for the time being so you can see what it is. But it looks like this. And I specified that we had a sample size of 8. So we would refer to that did not highlight. That section. So we have a sample size of 8. The critical value, according to that, is 0.707. Alright. And so because of that, we could then use that in our comparison on here. 0.939 is indeed greater than 0.707. So because of that, a positive linear relationship exists. Positive is in parentheses because technically it just says a linear relationship exists. But because this is positive, that's why I wrote positive. It's that same idea though. When it comes to these, this correlation, for any observational study, we could only say that we have correlation and that does not imply causation. Now we could call it correlation, we could call it association, same thing, but we cannot say causation for observational studies. That's all that this is basically saying. And one last example involving the correlation coefficient for this. We have a pediatrician who wants to determine the relation that may exist between a child's height and head circumference. She randomly selects 8 children, measures the height and head circumference, and obtains this data. Using the height to predict the head circumference, we want to determine the explanatory variable and the response variable. So the height here would be our explanatory variable, since we're using that to predict the head circumference, and the head circumference is our response variable. And then to compute this linear correlation coefficient, again, does not matter which one comes first in the sense of our correlation coefficient, but just show that in here very quickly. Let me bump myself over to this data, copy and paste that in, and then go to stat, summary stats, correlation again. Select these two, and that gives us a correlation coefficient of 0.7985. Hence where that came from for this last example. Thank you.